Okay, so module 14 is the transport layer. And of course, this is Introduction to Networks. Oops. And so, what are we going to look at today? So we're going to look at the transport layer. So we're going to look at the transportation of data and basically the transport layer's contribution to that. We'll look at TCP as an overview. We'll look at UDP as an overview as well. And then we'll look at port numbers, which are pretty consistent between TCP and UDP. We'll look at the TCP communication process, how it does reliability and flow control, and then we'll talk about how UDP communicates. And that's a lot less complex. Okay, so the transportation of data. So the transport layer is responsible for logical communications between applications running on different hosts. The link between the application layer and the lower layers that are responsible for network transmission. So you've got the application layer, of course, is what requests that transport to be done. And of course, it's the transport layer that receives it at the destination machine. Transport layer gives it to the application on the destination machine. So the responsibilities of a transport layer. And so tracking individual conversations, segmenting data and reassembling segments, adds its own header information. It identifies, separates, and manages multiple conversations, uses segmentation and multiplexing to enable different communication conversations to be interleaved on the same network. So IP does not specify how delivery or transportation of packets takes place. The transport layer protocols specify how to transfer messages between hosts and are responsible for managing reliability requirements of a conversation. So the transport layer includes the TCP and UDP protocols in the TCP/IP stack. And so TCP and UDP are very different. They do their jobs different ways. TCP is full-on reliability. It's the industrial strength version. The downside for TCP is it takes a while to set a connection up, and it takes a while to tear it down, and it's quite the control freak. While UDP is sort of quick and dirty, and so sometimes quick and dirty is actually better. And so when you're using VoIP, voice over IP, it uses UDP, because there's no sense of retransmitting data that got missed in a VoIP conversation, because it's just going to make the big pauses in the conversation, and then what's it going to have to catch up? And so it's going to have to run it fast, and so it just makes the voice conversations worse. And so UDP is good for those small processes. So DHCP uses UDP. DNS does, because it's just one packet request, one packet reply. You don't need the industrial strength of TCP to do that. And so some things UDP is just more sensible. Other things TCP is the more desired process. So TCP provides reliability and flow control. It numbers and tracks data segments transmitted to a specific host from a specific application. It acknowledges received data. It will retransmit any unacknowledged data from a certain amount after a certain amount of time. Sequence data that might arrive in the wrong order, and it will send data at an efficient rate that is acceptable by the receiver. So that's flow control, in other words. UDP provides the basic functions of delivering datagrams between the appropriate applications with very little overhead and data checking. And so it's connectionless. So with TCP, there's actually three-way handshake before any data moves. UDP doesn't bother with that. UDP is known as a best effort delivery protocol because there is no acknowledgement that the data is received at the destination. So the right transport layer for the right application. So UDP is also used by request and reply applications where the data is minimal and retransmission can be easily and quickly done. If it is important that all data arrives and it can be processed in its proper sequence, TCP is used as a transport protocol. So, web pages, well, you want all the web page, so TCP is good for that. Again, sending an email, you want all of your email, so again, you use TCP. FTP, file transfer protocol. Not much point transferring a file if you don't get all of it. So again, we use TCP. VoIP, well, as I explained earlier, recovering from lost bits of voice just makes the voice conversation worse, so we don't bother. DNS, again, as I said, one quick request message, one quick reply message. If it doesn't work the first time, we'll try it again. And yeah, DHCP and all kinds of things like that all use UDP. They're very small protocols. All right, so TCP in a little more detail. So it establishes a session. So TCP is connection-oriented protocol that negotiates and establishes a session. Don't know whether it's permanent, but it's fixed for a while between source and destination devices prior to forwarding any traffic. It ensures reliable delivery. For many reasons, it is possible for a segment to become corrupted or lost completely as it is transmitted over the network. TCP ensures that each segment that is sent by the source arrives at the destination. It provides same order delivery because networks may provide multiple routes that can have different transmission rates. Data can arrive at the destination in the wrong order, but because TCP puts segment numbers or numbers each of those segments, it can put it back into the correct order. UDP actually can't do that. And so that's what I mean. It does same order delivery doesn't mean it gets delivered to the host in the correct order. What it means is it gets delivered to the application in the correct order. When TCP's finished with it, it's in the correct order, and then it hands it up to the application. So supports flow control. So network hosts have limited resources, be that memory, processing power, bandwidth. And so TCP is aware that these resources can get overtaxed at times, and it can request that the sending application reduce the rate of data flow. That's not the only time as well. If too many packets start getting lost in transit, it will actually slow down the flow to try and minimize that loss. And so, obviously, there's a router, possibly a router somewhere in the path that's being overloaded, and it's having to drop packets because it can't forward them all. And so slowing down the flow will hopefully fix that. So what's the header look like in TCP? So now, of course, TCP doesn't do addressing. That's IP's job. But TCP needs to be able to identify what application at the source machine and what application at the destination machine need to use this communication. And so if you've got a web browser, the source port may well be some dynamic number, quite possibly higher than 65,000, because 16-bit number allows you to count to more than 65,000. But a destination port number, if you're talking to a web browser, well, that port number would be 80, because web servers listen on port 80. Also port 443 if you're doing secure web. And so basically, when a client connects, it will use some dynamic port number of its own, but it will normally use a well-known port number of the server that it's trying to connect to. And so, if it's trying to connect to email, it'll be port 25 as a destination. If it's trying to connect to a web browser, as I said, probably port 80, and so on. Now, that numbering that happens on TCP segments is looked after by this sequence number. So it's a 32-bit number. So you've got 34, don't know what that is. There's 4 billion you can count up to with that, so that's all very nice. And acknowledgement numbers are actually the sequence number, but from the opposite direction. So the sequence number, of course, is what the sending machine is doing. The acknowledgement number is actually acknowledging back to the other machine that, hey, I've received up to this sequence number actually, but we call it the acknowledgement number so you don't get them confused. And so then we have a header length field, control bits, and so things like SYN, SYNAC, and all kinds of things like that are in there. FIN, they're all control for what's happening with the conversation at the moment. So window is actually window size. That's actually the flow control. And then there's a checksum for the segment as well. And then there are other things for priority and things like that. So TCP records which information it has sent and which information has been acknowledged. And so that's what we use the sequence numbers and acknowledgement numbers for. Okay, so an explanation. I've pretty much explained most of these things. So sequence number is The 32-bit field used for reassembly purposes, so it tells you what part of this conversation this particular segment is. And the acknowledgement number is actually indicate that data has been received and the next byte expected from the source will be. So I've received this conversation up to byte number 2556, whatever it might be. So the header length is just the size of the TCP header. And so from there, there's the control bits, which we'll look at a bit later. Window size, as I said, is basically the number of bytes that will be accepted at any one time. And so the larger the window size, the faster the flow, basically. Checksum is error checking for both the header and the data. And urgent, as I said, it's about prioritizing. Now, with TCP, there are, and this is by no means an exhaustive list, certain protocols that use TCP. And so web pages, I've already mentioned that. FTP, file transfer, I've already said that. SMTP is mail, I've already said that. SSH I didn't mention, so of course that's a remote desktop based or remote terminal, and so of course you don't want to be missing out information on the terminal window either, so again you need reliability. And so TCP handles all tasks associated with dividing the data stream into segments, providing reliability, controlling data flow, and reordering segments. All right, so UDP. So UDP features include the following. Data is reconstructed in the order that it's received. It doesn't use segment numbering. Any segments that are lost are not resent. There is no session establishment. The sending is not informed about resource availability. Okay. So, as you can see, the header in UDP is a lot smaller. We have a source port, we have a destination port, we have the header length and a checksum, and that is it. Not a lot. And so, of course, the source port is the application port number for the sending machine. Destination, of course, is the port number for the receiving machine. Length is just the length of the header. And then the checksum, again, is you can detect whether there's been an error in transmission. Okay, your applications that use UDP. So DHCP, as I said, 2 packets sent, 2 packets received in DHCP, not very big. DNS, most requests are 1 packet sent, 1 received. SNMP, not greatly different. So that's Simple Network Management Protocol, SNMP. TFTP is Trivial File Transfer Protocol. Now that was actually originally created to transfer config information for an old equivalent of DHCP called BootP. If it needed to transfer larger amounts of configuration data, it would actually use TFTP to do that. So as I said, VoIP or voice over IP, again, reliability doesn't do it any favors. And video conferencing, again, yes, you might get the odd patchy bit on the picture and maybe the sound might drop out every now and then, but it's far better for that to happen than it to pause, recapture, and then try and catch up. No, so yeah, video conferencing is the same. So live video and multimedia applications. These applications can tolerate some data loss, but require little or no delay. Examples, VoIP and live streaming video. Simple request and reply applications, where the host sends a request and may or may not receive a reply. So DNS and DHCP are examples of that. And applications that handle reliability themselves. So unidirectional communications where flow control, error detection, acknowledgements, and error recovery is not required. It can be handled by the application. So SNMP and TFTP actually do their own reliability stuff. That's why they use UDP. But I've got to admit, TFTP is not as reliable as FTP. I've had the odd error using TFTP. So port numbers. So as you saw in both UDP and TCP packets, they have a source and destination port number stored in them. So the port number is associated with the originating application on the local host, whereas the destination port is associated with the destination application on the remote host. So we have some, now the term socket basically means a combination of IP address and port number. That's called a socket. So the source and destination ports are placed within the segment header. So here, source port, destination port. The segments are then encapsulated within an IP packet. The combination of source IP address and source port number, or destination IP address and destination port number, is known as a socket. That's how you plug into that computer, basically. So sockets enable multiple processes running on a client to distinguish themselves from each other, and multiple connections to a server process to distinguish from each other. So basically what we're saying here is this host has a client, an FTP client running, and it's requesting something from an FTP server. Now, FTP servers have a well-known port number of 21 used for their control messages, and that's why we use that as the destination number for the TCP header. Now, the source port was just a random number that hasn't been used previously on the client, but because the client creates the connection, it's the first one to do this communication. When it talks to the FTP server, well, the FTP server will see that, okay, that requesting client is using port 1305. And so when it replies to that client, it knows to make that the destination port number in its reply, much the same as it will use the source IP address from the client as the destination when it replies. So much the same idea. So, but of course, the server has to listen on port 21 because that is the default port number, and that's what the client will normally attempt to use. You can use a different port number, but the user will actually typically have to know that and type that in separately. And yeah, not that many people know that. So normally they just use the standard port. So also we have another conversation. So this server is not just an FTP server, it's a web server. And so this client machine also has a web browser running, and it wants to look at a web page on that server. And so again, that well-known port number for the destination is port 80, as I've said before. Again, the client picks its own unique number. It can't use port 80 because how many of us have more than one tab open in our browser? Pretty much all of us. Before there were multiple tab browsers, we used to have just multiple instances of the browser running. So anyway, you couldn't have used port 80 as the source because, hey, what's the other tab going to use? So that's why we use that random number, normally above 1,000, quite possibly above 65,000. And so because it's the client, again, that creates this connection, it will say, well, hey, my source port is 1099. And so when the server replies, it will know to make that the destination port on the reply message. Okay, so well-known ports are 0 to 1023. These port numbers are reserved for common or popular services and applications such as web browsers, email clients, remote access clients. Define well-known ports for common server applications enables clients to easily identify the associated port required. There are registered ports between 1024 and 49151. And so these port numbers are assigned by IANA to a requesting entity to use with specific processes or applications. These processes are primarily individual applications that a user has chosen to install, rather than common applications that would receive a well-known port number. And so, for example, Cisco has registered port 1812 for its Radius server authentication process. All right, so, and then there are private and dynamic port numbers. These are known as ephemeral ports. And so the client's OS usually assign port numbers dynamically when a connection to a service is initiated. The dynamic port number is then used to identify the client application during communication. And so that's when I was talking about for the FTP client software and the web browser software. Now, some well-known port numbers. 20 and 21 are used for FTP. Now, FTP is a bit of a strange one. Most applications only ever have one port number. FTP, in their wisdom, decided to use two. And the downside of that is it can often break many connections going through a firewall because suddenly it's using a different port number. And so you often have to load specialist modules in that firewall to actually accept that, hey, these port numbers might actually change. So stateful firewalls don't like FTP much. Anyway, so SSH, or Secure Shell, uses port 22. Telnet uses port 23. SMTP, which is how most mail is transported, uses port 25. DNS uses port 53. You'll notice that it says both UDP and TCP. Now, when you're a client and you make a DNS request, you will be using UDP. But servers actually do transfer information between one another. And so if you've got more than one server in the same domain naming area, it will actually use TCP to do zone transfers, so that, again, we want that to be reliable. We don't want missing information there. And so other ports are 67 and 68 for DHCP. TFTP uses 69. Web browsers use 80. 110 is used for POP3, which is an old email receiving protocol. IMAP is a newer one, which is 143. SNMP uses 161, and of course secure web pages use 443. That's, again, not an exhaustive list, but a good list. Okay, now we can actually use the command netstat to see what's going on. Now, if you just type in the plain netstat command, you get what active connections are happening at the moment. And so you can see that there are, this is our local computer's IP address, and these are the port numbers that are used by this client software. And you can see that we're talking to, looks like 5 different web browsers, or servers, I mean. Or at least there's 5 tabs open. And NetBIOS SSN, that is actually, must be a Microsoft client protocol, I think, NetBIOS. And so state is established. So basically there is a two-way connection between this host and those servers. And so it's an active, established connection. Now, with different options, Netstat can give you other information as well. Let's have a look. Yeah, so you can do something like Netstat. Netstat minus TU. Now, this may not work on Windows. I've got to admit. Oh, no, it doesn't like it. Which option doesn't it like? T doesn't like U. All right. Works nicely on Linux. Okay, these are all the ports that are open on my host. That's a lot, isn't it? Now you'll see that some should actually be quite possibly listening. Yeah, listening basically means my host is actually listening for other hosts to connect to it. Bit of a worry, that's a lot of port numbers. We're listening on 443. I'm wondering what people have installed on this machine. Anyway, might have a look into that. This is more than what you normally get. And so basically listening means that my machine is actually trying to be a server in some instances. It's sitting there waiting for someone to connect. So 443, that is, yeah, that's a secure web server. So I'm not sure what that is. I might actually have a bit of a play with that later. I've just put that to one side. So you can actually see what your host is doing. And so when I did TUA, T means, no, it wasn't TUA, I did TNA, didn't I? So T means TCP, all TCP services. N means show me the number. You'll notice here that this one shows us HTTP. If they'd done Netstat minus N, it would have actually shown 80 for those as well. And I think it would have been the 445 there for the NetBIOS. And so it actually tells you the port number instead of the descriptive name. And A means all connections. And so that was why I got all those listening port numbers. But yeah, very strange that this machine's doing so much. Anyway, I'm going to have another look. So TCP communication process. And so the TCP server process, each application process running on a server is configured to use a port number. An individual server cannot have two services assigned to the same port number with the same transport layer services. An active server application assigned to a specific port is considered open, which means that the transport layer accepts and processes segments addressed to that port number. Any income client request addressed to that correct socket is accepted, and the data is passed on to the server application. So basically, as you can see, we've got a server here. It's listening on both port 80 and port 25. So it's a web server and it's a mail server. And so we've got this client hooking to the web server. We've got this client hooking to the email server. Now, to establish a connection, there's what's called a three-way handshake. I might have mentioned it previously. And so the initiating client requests a client to server session with a server. And so that is what's called a SYN packet, which is actually short for synchronize. And that's one of those control flags in the TCP header. There's a bit there that if you set that, that means that this is a SYN packet. And so then the server acknowledges the client to server communication session and requests the server to client communication session. So that's basically the SYN will open up that other one, and the acknowledge says, hey, yeah, cool, I see that, I'm all right for that to happen. And so then the client then sends the last packet in the three-way handshake, which is purely an acknowledgement packet, saying, yeah, all right, I acknowledge your SYN request. And so there's been a SYN go in both directions and an acknowledgement go in both directions, just that one of them did both at the same time. All right, now that's how you open a connection to a server. Then after that's happened, you can then start transferring data, whatever it might be. So be that a web page or a file from FTP or whatever it might be. So you've established a connection, and there's more than just the SYN and ACK going on. There's the flow control information. We actually initialize the sequence numbers and so on and so forth. All happens during that three-way handshake. And so then once that's done, we can then start transmitting the data. When we're finished, well, then we need to close the connection. That's why when it said permanent, well, you know, we do close the connections as well. And so with to terminate a session, there's actually 4 segments that are sent. So when the client has no more data to send in the stream, it sends a segment with the FIN flag set. So that's another flag. So we've already seen 3 of those flags. There's SYN, FIN, and acknowledgement we've seen. There are some more as well, but they're the ones we've seen so far. And so we say, I want to finish this connection. And so we send that packet. Then the server acknowledges. So, yeah, cool, I've received that. And then the server will actually send its own FIN packet saying, yeah, I need to close it as well. There's nothing more for me. And then the client will then acknowledge that. And then now our connection is closed. So it's a nice, polite system, TCP. And so the three-way handshake, of course, was that first one. It establishes that the destination device is present on the network. That's always nice. You know that the machine is there and is able to respond to you. It verifies that the destination device has an active service and is accepting requests on the destination port number. And then it informs the destination device that the source client intends to establish a communication session on that port number. After the communication is completed, the sessions are closed and the connection is terminated. So the connection and session mechanisms enable TCP reliability functions. So if either machine has outstanding stuff that needs done, it won't do the FIN until that's been done. And so it's a nice, polite communication. So the through a handshake, you could sort of say as your, hellos, and then the FIN is your polite goodbyes. And so it's a nice, way to have a conversation. Now, talking about all those flags that we were talking about. So there's the SYN flag, the FIN flag, and the acknowledgement flag we've spoken about. Well, there are a few others as well. So there's an urgent field. And so basically there's 6 bits set aside for this. And so there's 1, 2, 3, 4, 5, 6. And so there's also a reset and a push And so reset resets a connection, and push will just, I think, just get it to move some data. And so, yeah, so there are some flags that are in there. And if you look at Wireshark, it will actually show you those flags. It will actually show you which ones have been set. So it's quite nice for that. Okay, reliability and flow control. So TCP can also help maintain the flow of packets so that devices do not become overloaded. There may be times when TCP segments do not arrive at their destination or arrive out of order. All the data must be received, and data in these segments must be reassembled into the original order. Sequence numbers are assigned in the header of each packet to achieve this goal. Pretty much already spoken about that. So, of course, the transmitting machine will send it in order, but networks are complex, and some load balancing might happen across different links. And so here they're arriving out of order. So 6 has arrived way before 3, 4, and 5. And so, yeah, we need to put them back into order. Now, that's nice. And so reliability. So no matter how well designed a network is, data loss occasionally occurs. TCP provides methods of managing these segment losses. Among these is a mechanism to retransmit segments for unacknowledged data. And so basically, A is transmitting to B, and then segments 3 and 4 got lost. Now, basically what's going to... Now, these acknowledgements, the acknowledgement actually says, I'm expecting segment 3 next. So basically B is received 2 and has got nothing else, or at least it hasn't gotten 3 and 4. And so the acknowledgement numbers are actually saying the bit of data I'm expecting next is segment 3. And so that's when you can see that 3 got resent, and so away it went. Now, so as you can see here, host operating systems today typically employ an optional TCP feature called Selective Acknowledgement, negotiated during the three-way handshake. If both hosts support that, the receiver can explicitly acknowledge which segments or bytes were received, including any discontinuous segments. So previously, basically, it would have actually had to, with 3 and 4 going missing, it would have actually had to go and start from 3 and keep going. But with more modern hosts, you can actually do selective acknowledgement and just say, hey, look, I missed 3 and 4. And so basically, acknowledgement, I'm expecting 3 next, but hey, I don't really need to see 5 through to 10. I've already seen that. And so we'll just do 3, 4, then 11. And so it's a little more efficient. Now, flow control. TCP also provides mechanisms for flow control as follows. Flow control is the amount of data that destination can receive and process reliably. Flow control helps maintain the reliability of TCP transmission by adjusting the rate of flow between source and destination for a given session. So basically, the first thing that happens is they actually look at the maximum segment size. And so that's basically, what size chunk of data can I send at any one time? And so that's actually set during the three-way handshake. Also, the window size, as I said, the flow control is negotiated at the same time. Now, when you acknowledge, you actually confirm this information. So you acknowledge saying, now acknowledgements also aren't, you don't actually number the segments 1, 2, 3, 4. You actually number them by the byte number. And so let's just say you've got 10,000 bytes to send. The first one is 1,500 bytes. So the first packet will actually be number 1. The next one will be 1,501. The next one will be 3,001. And so we'll actually climb by the size of the segments. So that's what we're seeing here, except it's not 1,500, it's 1,460. I was just trying to make it easy for myself. And so that's the acknowledgement is saying, hey, look, I've received 2920. The next bit I'm expecting is 2921. So that's expectational acknowledgement. And so then they'll send 2921. All right, now I'm expecting 4381 because 4380 arrived and so on. Now the window size can actually modify, and so if things are getting through to that host rather slowly, it can actually decrease the window size. Now, has anyone ever noticed the pattern when you're downloading a big file that the speed will vary, won't it? So you'll start the download, it'll start pretty slow, then it'll speed up, and then it might slow down a bit, and then it might sort of cycle up and down, mightn't it? And so basically, most TCP/IP settings are pretty conservative, and so in Windows, I think there's actually an entry in the registry that actually says what's your initial window size going to be, and so you can actually modify that if you're a bit of a geek. And so basically, that's what your host will negotiate first. I want a window size of XYZ, and then if it starts downloading at that speed and there's nothing going wrong, it will actually up the window size, and so that's when your download starts increasing in speed. Still no problems? I'll up the window size again. Great. And it will keep upping it until then segments start getting lost, and it will then down the window size a little bit. So, all right, well, that was asking a bit much, and so I'll down the window size, and so it'll slow down a bit. Then when it settles into no errors, it'll sit there for a while. And, well, maybe the congestion's gone now. Let's try that bigger window size again and see if we can push it higher. And so that's basically what happens with your downloads. That's how the speed varies. It's all through this feedback mechanism of window size inside the acknowledgement, inside the TCP header. So that's what controls your speed of download. Of course, congestion is another major factor, but but it's actually it's cycling through different window sizes is what changes your download speed. Okay, so the maximum segment size is the maximum amount of data that the destination can receive. And so it's 1460 when using IPv4. A host determines the value of its MSS by subtracting the IP and TCP headers from the Ethernet maximum transmission unit of 1500. And so that's how it ends up being 1460. So that's how big a chunks you chop that data into when you create segments. And so when congestion occurs in a network, it results in packets being discarded by an overloaded router. To avoid and control congestion, TCP employs several congestion handling mechanisms, timers, and algorithms. So we're looking at the acknowledgement going back, saying, well, I'm expecting to see 2 next. Now, the sending machine can actually say, well, I'm not getting the acknowledgements I expect from the destination machine. There's obviously lots of packets dropping out, and so that's when you reduce the window size. Okay, so Udp communication, this will be quick. It does not establish a selection, so there's connection. There is no three-way handshake with UDP. It provides low overhead data transport because it has small datagram header and no network management traffic. So basically with UDP, you put in a source IP address, you put in a destination IP address, destination port number, you send it on a network and hope like hell it gets there. That's UDP. So it does not track sequence numbers. It has no way to reorder the datagrams in their transmission order. It simply reassembles the data in the order that it was received and then forwards it to an application. So if it's gone over their complex network and arrived in a strange order, well, that's the order it's coming to the application in. Now, that higher application might be able to reorder it, or it might not. So UDP service-based applications are assigned well-known registered port numbers. UDP receives a datagram destined for one of these ports. It forwards the application data to the appropriate application based on its port number. So, of course, DNS request, destination of port 53. When it arrives at the server, if it's got a DNS server running, it will pass it on to that. UDP client process dynamically selects a port number from the range of port numbers and uses this as the source port. Again, because it's the client that initiates the connection, all the server needs to do is record the source port number and use that as a destination for returning it. The destination port is usually a well-known or registered port number. After a client has selected the source and destination ports, the same pair of ports are used in the header of all datagrams in that transaction. Okay, that's enough for the transport layer. So, what did we talk about? So the transport layer is a link between the application layer and the lower layers that are responsible for network transmission. And so the options for the transport layer are TCP and UDP. TCP establishes sessions, ensures reliability, provides same order delivery, and supports flow control. UDP is simple, but it provides basic transport layer functions. Not much. And so UDP reconstructs data in the order it's received. Lost segments are not resent. No session establishment. UDP does not inform the sender of resource availability. TCP and UDP transport layer protocols use port numbers to manage multiple simultaneous conversations. Each application process running on a server is configured to use a port number. The port number is either automatically assigned or configured manually by a system administrator. For the original message to be understood by the recipient, all the data must be received. The data in these segments must be reassembled in the original order. Sequence numbers are assigned in the header of each packet. Flow control helps maintain reliability of TCP transmission by adjusting the rate of data flow between source and destination. A source might be transmitting 1460 bytes of data within each TCP segment. This is the typical MSS, or maximum segment size, that a destination device can receive. The process of the destination sending acknowledgements as it processes bytes received, and the continual adjustment of the source's send window is known as sliding windows. That's the flow control method. It's not sliding doors, it's sliding windows. To avoid and control congestion, TCP employs several congestion handling mechanisms. So there's the logo. So that's it for chapter 14. So I think chapter 15 is the application layer. So we actually have done enough depth in UDP and TCP in that session. So we don't have an extra chapter for that. So, well, see you then. All right.